Welcome to Night Lesson. Relax and learn along the way.
Intro: The Child Who Taught His Teachers, the story of Carl Friedrich Gauss. Good evening, and welcome to a journey into the past, a journey into the world of numbers, of stars, and of the invisible forces that shape our world. Close your eyes for a moment and let the sounds of the day slowly fade away. Breathe in deeply, and then slowly out again. Feel the tension of the day fall away from you, giving way to a gentle calm. Tonight we follow in the footsteps of a mind that shone so brightly, its light still illuminates the paths of science centuries later. It is the story of Carl Friedrich Gauss, often called the Prince of Mathematicians. Yet our story begins not in the splendor of a throne room, but in the humble cottage of a laborer in the old Duchy of Brunswick. Imagine a world in transition, the late 18th century, a time without electric light, without the roar of engines, a time when the nights were still truly dark and the starry sky shone in all its majestic glory. It was an era of upheaval, in which the old orders of Europe began to tremble, and the ideas of the Enlightenment fell like seeds on fertile ground. In the salons, reason and progress were debated, but for most people life was hard, simple, and determined by the work of their hands. It was into this world, in the year 1777, that our protagonist was born, a child whose mind was destined to shatter the boundaries of human knowledge. Our tale is not one of dramatic battles or thrilling adventures. It is a quiet, contemplative story. It is the story of an inner universe, of a mind that found a beauty and an order in the abstract patterns of numbers, more profound than anything the visible world seemed to offer. It is the story of moments of quiet reflection, of nights spent calculating by candlelight, of the persistent, almost meditative search for truth in a language that needs no words, the language of mathematics. We will see how a boy who could barely read and write, but who could already calculate in his head, became a man who would redefine the measure of the world. Let us immerse ourselves together in this time. We will hear the soft scratching of styluses on slate boards, smell the scent of old paper and bound leather in the libraries, and feel the cool night wind on the mountain peaks from which Gauss surveyed the land. We will witness how a single brilliant idea, born in the silence of a study, could revolutionize astronomy, and how curiosity about the invisible force of a magnet would lead to the invention of the telegraph. It is a journey that will take us from the fundamentals of arithmetic to the very limits of our conception of space and time. This story is an invitation to reflect on the nature of genius. Was it a divine spark, or was it the result of tireless work, of a discipline and concentration that are almost unimaginable for us today? Perhaps it is a mixture of both, an extraordinary gift that met an equally extraordinary character, modest, persistent, and incorruptible in his pursuit of knowledge. A story that reminds us that the greatest revolutions often do not happen loudly and boisterously, but in the deep silence of thought. So take another deep breath and let yourself drift into the world of Carl Friedrich Gauss, the child who taught his teachers and changed the world of science forever. Chapter 1: A Spark in the Darkness. We begin our journey on April 30th, 1777 in Brunswick, a city of winding alleys, half-timbered houses, and the gentle lapping of the Oak River. In a small, inconspicuous house on Wilhelmstrasse, a boy is born who is given the name Johann Carl Friedrich Gauss. His family does not belong to the nobility, nor to the educated bourgeoisie. His father, Gebhard Dietrich Gauss, is a man of simple but honest labor. He works as a gardener, a butcher, a bricklayer, and a canal cleaner, a man whose hands are marked by hard physical work and whose mind is focused on the practical, the tangible. He is a strict, sometimes gruff man, who has little understanding for the dreamy, intellectual world of his son. He wants a solid trade for Carl Friedrich, a secure livelihood. The world of numbers and letters seems to him a fruitless art. The mother, Dorothea Bensi, is quite different. She is an intelligent, sensitive woman with a sharp mind, who, however, never had the opportunity to receive a formal education. She can barely write, but she recognizes her son's extraordinary gift early on. She becomes his first and most important advocate, a silent force who defends him against the pragmatic plans of his father. Imagine the evenings in the small living room. The father, tired from work, and little Carl Friedrich, perhaps only 3 years old, watching his father tally the payroll, and in a quiet voice, correcting a mistake in the adult's mental arithmetic. An anecdote that Gauss himself would later often tell, a first glimmer of that incredible talent. He had learned to calculate before he knew the alphabet, simply by listening and observing. At the age of 7, Carl Friedrich enters St. Catherine's School, a public school for the children of the poorer classes. The instruction is characterized by drill and monotony. The teacher, J.G. Butner, is a man past his prime, often keen to keep his 100 or so pupils busy with long mechanical tasks in order to get some peace and quiet for himself. One day, as the legend that has become a founding myth of mathematics goes, Butner gives the class a task meant to occupy them for a considerable time. He asks them to add up all the numbers from 1 to 100, 1 plus 2 plus 3, and so on, up to 100. The pupils immediately begin to scribble on their slates with their styluses, laboriously adding number after number, a race of concentration against boredom and the inevitable calculation errors. But scarcely has the teacher finished stating the problem when, after just a few moments, little Gauss stands up, walks to the front, lays his slate on the teacher's desk, and says in Low German, "Liegt sei, there it lies." He returns to his seat and waits with his arms crossed while the rest of the class is still sweating and calculating. The teacher Butner casts a disdainful glance at the slate, convinced the boy is just playing a prank. But after a long time, when he collects the slates of the other pupils, all of which have different, mostly incorrect results, he looks at Gauss's slate. On it is a single number, 5050, the correct result. Butner is stunned. How could this little boy have done it in such a short time? He asks him, and Gauss explains his method, a method of such elegant simplicity that it deeply impresses the teacher. Instead of adding the numbers in sequence, his mind had instantly recognized a deeper pattern. He had noticed that the first and the last number, 1 plus 100, add up to 101. So do the second and the second to last number, 2 plus 99, which also make 101, and the third to last, 3 plus 98, again 101. This pattern continues. There are exactly 50 such pairs, 100 divided by 2. So the total sum must simply be 50 times 101, which is exactly 5050. In that moment Butner realized that he was not dealing with an ordinary student. This little boy from a poor background had not just solved a problem. He had discovered a mathematical principle, the formula for the arithmetic series. It was a spark of pure genius that lit up the dusty air of a crowded classroom. This single moment of insight was to change the entire course of Carl Friedrich Gauss's life and open the doors to a world his parents would never have even dared to dream of. Chapter 2: A Duke's Discovery. The incident with the summation problem at St. Catherine's School was more than just an anecdote. It was a wake-up call for the teacher Butner. He understood that his own knowledge was insufficient to nurture this extraordinary talent. He did something remarkable. He acknowledged his limits and took action. At his own expense, he ordered a better arithmetic book from Hamburg and gave it to the young Gauss. But Carl Friedrich worked through it so quickly that Butner soon resignedly stated, "I can teach him nothing more." At this point, a second important figure enters the scene, Martin Bartels, Butner's young assistant. Bartels himself was an enthusiastic amateur mathematician and only a few years older than Gauss. A friendship developed between the boy and the young man, based on their shared love for numbers. Imagine the two of them, sitting together after class, poring over problems that went far beyond the school curriculum. They studied the works of Leonhard Euler and Isaac Newton together, delving into the secrets of algebra and infinite series. Bartels was not so much a teacher to Gauss as a sparring partner, a first intellectual companion who could keep up with the speed and depth of Gauss's thoughts. It is Bartels who makes the crucial connections to the influential Society of Brunswick. He knows some officials and professors and tells them about the child prodigy from the working class. The rumor of a boy whose mind shines like an uncut diamond begins to circulate in the educated circles of the city. Thus, the news eventually reaches the court of Charles William Ferdinand, the reigning Duke of Brunswick-Wolfenbüttel. The Duke was a typical representative of enlightened absolutism, a man interested in art, science, and the welfare of his land. He was a nephew of Frederick the Great and had fought in the 7 Years' War. The idea of discovering and fostering an extraordinary talent among his subjects fit perfectly with his self-image as a wise and modern ruler. He summoned the young Gauss to him. Picture the scene. Carl Friedrich, about 14 years old, perhaps in his best but still simple clothes, stands shyly and reverently in the Duke's magnificent palace. Surrounded by silk, gold, and wigs, he presents his skills to the sovereign. The Duke and his advisors give him mathematical problems, and Gauss solves them with a speed and confidence that astonishes those present. The Duke is deeply impressed. He sees not just the boy, he sees an investment in the future and glory of his duchy. He makes a decision that will change Gauss's life forever. He decides to cover the costs of his further education. In the 18th century, this ducal patronage was the only way for someone from Gauss's class to attain a higher education. It was like winning a lottery, granting him access to a world that would have otherwise remained forever closed to him. From 1792 to 1795, the Duke financed his attendance at the Collegium Carolinum in Brunswick, a type of technical university. Here, for the first time, Gauss received systematic instruction at the highest level. He devoured the works of the great mathematicians and learned the classical languages, Latin and Greek, so perfectly that he could read and write them fluently. His teacher of ancient languages, a man named Zimmermann, was as impressed by his linguistic abilities as his mathematics teachers were by his computational skills. In these years, Gauss laid the foundation for his later work. He did not just study, he was already conducting research. In his notebooks from this period one can find the seeds of his greatest discoveries, such as the method of least squares and initial conjectures on the distribution of prime numbers. The Duke had discovered a rough diamond, and under the care of the best teachers in the land, this diamond began to be cut, revealing its inner fire. The financial security the Duke provided freed his mind from the worries of daily life and allowed him to devote himself entirely to the unfolding of his incredible intellectual potential. Chapter 3: The Years of Learning. After Gauss left the Collegium Carolinum in Brunswick with an impressive foundation of knowledge, the next stage of his academic career awaited. The Duke, whose confidence in his protégé grew steadily, financed his studies at the renowned University of Göttingen starting in 1795. At that time, Göttingen was a center of the German Enlightenment, a university known for its excellent library and its relatively free intellectual spirit. For the young Gauss, this was like entering an intellectual paradise. He had access to a seemingly endless amount of knowledge, to the writings of the greatest thinkers in history. During this period, a remarkable inner struggle took place. Gauss, the master of numbers, was unsure which field he should dedicate his life to. His talent was so universal that he excelled not only in mathematics but also in philology, the science of ancient languages and texts. He read the Greek and Roman classics in the original with an ease and a deep understanding that amazed his professors. He loved the clarity and logical structure of Latin, a language in which he would later compose many of his scientific treatises. For a while, he seriously weighed whether he should become a famous classical scholar instead of a mathematician. Imagine this internal conflict: two worlds vying for the favor of a single mind, the world of poetic words and the world of abstract numbers. The decision was made on March 30, 1796. On this day, Gauss made a discovery that would shake the mathematical world and irrevocably seal his own path. It was a problem that had remained unsolved for over 2,000 years. Since the days of the ancient Greeks, since Euclid wrote his Elements, it was known how to construct certain regular polygons using only a compass and straightedge. These included the triangle, the square, the pentagon, and the 15-sided polygon, as well as all polygons that arise from repeatedly doubling the number of sides. But the construction of other simple polygons, such as the 7-sided or 11-sided ones, seemed impossible. Gauss, just 19 years old, proved on that memorable day that the construction of a regular 17-sided polygon, a heptadecagon, is possible with only a compass and straightedge. This was not an accidental discovery. It was the result of deep insights into the theory of cyclotomic equations, a field of algebra. He found that a regular n-sided polygon is constructible with compass and straightedge if and only if the number of sides n is a power of 2, or the product of a power of 2 and 1 or more distinct Fermat primes. A Fermat prime is a prime number of the form 2 to the power of 2 to the power of k plus 1. The 17-sided polygon was the first new case to be found since antiquity. 17 is such a prime for k equals 2, because 2 to the power of 2 squared plus 1 is 17. This discovery was of such fundamental importance that Gauss decided to dedicate his life to mathematics. His joy over this breakthrough was so great that he requested that the symbol of the regular 17-sided polygon be chiseled on his tombstone later. It was the moment the philologist within him finally gave way to the mathematician. From that day on, he began to keep a scientific diary, a thin booklet of only 19 pages, in which, over the following years, he recorded 146 of his most important discoveries in short, often cryptic notes. This diary is now one of the most valuable documents in the history of science, a window into the workshop of a genius. The discovery of the constructibility of the heptadecagon was the first entry. It was the starting signal for an unprecedented scientific career, which began in the quiet halls of the Göttingen Library. Chapter 4, the Disquisitiones Arithmeticae. Once the decision for mathematics was made, Gauss threw himself into his work with incredible energy. While still a student in Göttingen, and shortly thereafter, back in Brunswick and still supported by the Duke, he worked on his first great masterpiece. In 1801, at the age of just 24, he published a book that would change mathematics forever. The Disquisitiones Arithmeticae, or Arithmetical Investigations. This book, written in elegant, precise Latin, was far more than just a collection of calculation rules. It was the birth certificate of modern number theory, that branch of mathematics which Gauss himself called the Queen of the Sciences. Imagine an old, venerable building where many great masters over the centuries have furnished individual beautiful rooms, but without a clear plan for the entire structure. That was roughly the state of number theory before Gauss. There were many fascinating but isolated results from mathematicians like Fermat, Euler, and Lagrange. Gauss entered this building, recognized the hidden structures, and created a logical, cohesive masterwork of breathtaking beauty and depth. The Disquisitiones was not simply a summary of what was already known, it was a complete reconceptualization of the field. The heart of the book is the theory of congruences. Gauss introduced a new notation that revolutionized working with remainders. The symbol A as defined as B, mod m, means that A and B leave the same remainder when divided by m. This sounds simple at first, almost trivial. It is the mathematics of a clock. If it is 10 o'clock now, in 4 hours it will be 2 o'clock. In clock arithmetic, 10 plus 4 is not 14 but 2, or in other words 14 is congruent to 2 modulo 12. Gauss realized that this modular arithmetic was an incredibly powerful tool. He built a complete theory upon it, which allowed him to solve old difficult problems with a new, astonishing elegance. One of the jewels of the book is the first complete proof of the fundamental theorem of algebra, which states that every polynomial equation has a solution in the complex numbers. Others had attempted this before him, but their proofs had gaps. Gauss presented a rigorous proof and returned to this theorem throughout his life to find other, different proofs, as if he wanted to illuminate the problem from all sides. However, the absolute showpiece of the Disquisitiones is what Gauss called the Theorema Aureum, the Golden Theorem, the law of quadratic reciprocity. This theorem establishes a deep and surprising relationship between prime numbers. It makes a statement about whether one number is a quadratic residue of another, connecting the solvability of the equation x squared as defined as p, mod q, with the solvability of x squared as defined as q, mod p. The exact formulation is subtle, but the essence is a hidden symmetry in the realm of prime numbers. Euler had conjectured the theorem. Legendre had attempted a flawed proof, but only Gauss succeeded in providing a flawless proof. And not just one. He was so fascinated by this theorem that he found a total of 8 different proofs for it over the course of his life. The Disquisitiones Arithmeticae was not an easy book to read. The density of ideas, the rigor of the proofs, and the lack of examples made it a challenge even for experienced mathematicians. It was said that the book was like a fox that erases its tracks in the sand with its tail. Gauss presented the finished, polished results, but rarely gave hints as to how he had arrived at them. Nevertheless, the book became the Bible of number theory for the entire 19th century. It laid the foundation upon which generations of mathematicians would build. With this single work, the 24-year-old son of a gardener had established himself as the undisputed king of the Queen of the Sciences. Chapter 5: A Comet in the Sky. While Gauss was reorganizing the foundations of pure mathematics with his Disquisitiones Arithmeticae, an event in the night sky would soon catapult him onto a completely different stage and bring him worldwide fame. This story begins on the night of January 1, 1801, the first day of the new century. The Italian astronomer Giuseppe Piazzi, from his observatory in Palermo, discovers a new star-like object in the sky. He observes it over several nights and notices that it is moving. It could not be a fixed star. He initially suspects it is a new comet. He tracks its path for 41 days until the object moves too close to the sun and disappears in the glare of our central star. Piazzi falls ill, and by the time he can resume his observations, the celestial object is gone. News of the discovery spreads like wildfire through the astronomical community of Europe. It is agreed that Piazzi has found something significant, perhaps even the long-suspected planet that, according to the Titius-Bode law, should exist in the gap between Mars and Jupiter, but now it was lost. The problem was immense. From the few observational data points Piazzi had collected over a short period, the complete orbit of the celestial body had to be calculated to predict where and when it would reappear in the night sky after its journey behind the sun. The methods for orbit calculation known at the time, which dated back to Newton, were unsuitable for such a short observation period and so few data points. The best astronomers and mathematicians in Europe struggled with the problem. Their calculations produced such varied results that the search seemed hopeless. This is where the 24-year-old Gauss enters the scene. The news of the lost celestial body reaches him in Brunswick. The problem fascinates him. It is a perfect blend of abstract mathematics and concrete application. Years before, during his studies in Göttingen, he had already developed a new, powerful method for data analysis, which he had not yet published. The method of least squares. Imagine you have a series of measurement points that do not lie exactly on a straight line or a perfect curve, because every measurement contains small, unavoidable errors. The method of least squares now finds the curve that best fits the inaccurate data. Best in this case means that the sum of the squares of the deviations of the measurement points from the curve is made as small as possible. Gauss applies his method to Piazzi's sparse observational data. While other astronomers despair, he throws himself into the calculations with his characteristic concentration. He works for months, refining his algorithms and taking into account the complex perturbations caused by the gravitational pull of the large planets. Finally, in the late autumn of 1801, he publishes his prediction. He gives astronomers a precise region of the sky where they should look. Many are skeptical. Who is this young mathematician from Brunswick who claims to have solved a problem that has stumped the most famous astronomers? But one of the leading German astronomers, Franz Xaver von Zach, takes Gauss's prediction seriously. On the night of December 7, 1801, he points his telescope to the exact position indicated by Gauss. Success eludes him at first, but he does not give up. Finally, on New Year's Eve, December 31, 1801, almost exactly 1 year after its initial discovery, Heinrich Olbers in Bremen rediscovers the celestial body. It is only half a degree away from the position predicted by Gauss. It is a triumph. The rediscovered celestial body is named Ceres Ferdinandea at Piazzi's request, Ceres after the Roman patron goddess of Sicily, and Ferdinandea in honor of the King of Naples. Later, the name is shortened to Ceres. Today, we know that Ceres is the largest asteroid in the asteroid belt, a dwarf planet. But the true star of this story is Gauss. Overnight, he is famous throughout Europe. He has not only solved an astronomical puzzle, he has created a method that would revolutionize astronomy and every other science that relies on imprecise measurements. The young man who had fathomed the secrets of prime numbers had now also shown that he could tame the motion of celestial bodies with unprecedented precision. Chapter 6: The Director of the Observatory. The triumph of rediscovering Ceres had a lasting impact on Carl Friedrich Gauss's life. He was no longer known only in the narrow circles of mathematicians, but was a European celebrity. Scientific academies across Europe vied for him, and he received several tempting offers, including a call to the Academy of Sciences in St. Petersburg. His loyal patron, the Duke of Brunswick, was alarmed at the thought of losing his jewel. He increased Gauss's annual pension and promised to establish a new observatory for him in Brunswick. But fate had other plans. In 1806, at the Battle of Jena Arstedt, the Duke was severely wounded while serving as a Prussian field marshal, and died shortly thereafter. Gauss lost his longtime patron and friend. The future in Brunswick had become uncertain. In this situation, an offer from Göttingen came at just the right time. The university where he had studied offered him the position of director of the new observatory to be built, combined with a professorship. In November 1807, Gauss moved with his family to Göttingen, a city that would remain his home for the rest of his life. He was now an established professor, a civil servant with a secure income and a respected position. The restless years of dependency were over. His life in Göttingen took on a new, quieter, and more stable form. Imagine his daily routine. He rose early, often dedicating himself to his research even before breakfast, then held lectures for a small, hand-picked group of students, and spent hours and nights in the observatory with observations and calculations. He was not a captivating speaker. His lectures were demanding and aimed only at the most capable students. He detested teaching beginners the basics, but when he found a truly talented student, he supported him with great dedication. However, this phase of professional success was overshadowed by deep personal sorrow. In 1805, he had married Johanna Osthoff, a woman he described as beautiful, witty, and kind-hearted. It was a happy and loving marriage, from which 3 children were born. But the happiness was short-lived. In 1809, after the birth of their 3rd child, Johanna died from complications of childbirth. Their youngest son died only a few months later. Gauss fell into a deep depression. In his scientific diary, he wrote that the heavens now seemed empty to him and the world had become alien. The pain of this loss would accompany him for the rest of his life. To give his remaining children a mother again, he remarried the following year. His second wife, Minna Waldeck, was his late wife's best friend. This marriage, however, was of a different nature. It was more a decision of reason than a passionate love affair. Minna was often ill and suffered from melancholy. Although this marriage also produced 3 children, domestic life for Gauss often remained a source of worry. He increasingly escaped into the clear, orderly, and controllable world of his scientific work. The observatory became his refuge, a place where the laws of celestial mechanics applied, not the unpredictable storms of the human heart. During these years he published his second great work, the Theoria Motus Corporum Coelestium, Theory of the Motion of Heavenly Bodies, in which he detailed his methods for orbit calculation that he had developed for Ceres. The book became the standard work of theoretical astronomy. Thus the image of the reclusive scholar, the professor who rarely traveled, and whose universe consisted of his family, his study, and the infinite expanse of the sky above the observatory, was established in Göttingen. These were years of quiet but tireless productivity, in which Gauss significantly shaped the astronomy of the 19th century. Chapter 7. The measurement of the world. After Gauss had measured the orbits of celestial bodies with a new precision, he turned his mind to a seemingly much more down-to-earth problem: the measurement of the Earth itself. In 1818, he was commissioned by the King of Hanover to conduct a geodetic survey of the entire Kingdom of Hanover. Geodesy is the science of measuring and mapping the Earth's surface. The goal was to create a precise network of survey points to produce accurate maps, a task of great military and economic importance. What began as a practical commissioned work would lead Gauss to some of his deepest and most far-reaching mathematical discoveries. This work was not a quiet brooding in a study. For over a decade, Gauss spent many weeks and months of the year outdoors, traveling on horseback or on foot. Imagine the famous professor standing on the peaks of the Harz Mountains, on the Brocken, the Hohenhagen, or the Inselsberg, looking through the lenses of his theodolites. The method he used was triangulation. One measures the length of a single baseline on the ground very accurately. From the endpoints of this line, a third distant point is sighted, for example, a church steeple or a mountain peak. From the length of the baseline and the 2 measured angles, the entire triangle can be calculated. From this new point, One can then cite other points, and so, step by step, cover the entire country with a network of triangles. The practical execution was arduous and demanding. The weather did not always cooperate. Visibility was often obscured by haze or rain. To enable precise measurements even over very large distances of several tens of kilometers, Gauss invented a brilliant new instrument, the heliotrope. It was essentially a small movable mirror that caught the sunlight and directed it as a bright sparkling flash of light precisely to the observer at the other end of the triangle's side. Even from a distance of 100 kilometers, this point of light was still visible as a tiny but clear star on the horizon. This allowed Gauss to conduct his measurements with a previously unattainable accuracy. This practical work on the body of the Earth raised deep theoretical questions in his mind. The Earth is not a flat plane, it is a curved surface. The triangles he measured were not plane triangles, but spherical ones. The sum of their angles is not exactly 180 degrees, but always slightly more. This angular excess, the so-called spherical excess, is greater the larger the triangle is. Gauss began to think about the nature of curved surfaces in general. This led him to the creation of a completely new field of mathematics, differential geometry. His perhaps most astonishing result in this field he himself called the theorema egregium, the remarkable theorem. It states that the curvature of a surface is an intrinsic property. This means that one can measure the curvature without ever leaving the surface and looking into a surrounding three-dimensional space. Imagine a tiny two-dimensional creature living on a sheet of paper. As long as the paper is flat, its world is uncurved. If you now roll the paper into a cylinder, nothing changes for the creature in terms of local geometry. It can still draw the same plane triangles. A cylinder has an extrinsic curvature. It is bent in space, but no intrinsic curvature. It is different if the surface is a sphere. Every tiny piece of a sphere's surface is intrinsically curved. The creature could determine this by drawing a triangle and measuring that the sum of its angles is more than 180 degrees. This realization that curvature is a local measurable property was revolutionary. It freed geometry from the rigid corset of Euclidean space and opened the door to a whole new world of conceivable geometries. The survey of the Kingdom of Hanover had led Gauss not only to better maps, but also to the fundamental concepts that, almost a century later, Albert Einstein would need to formulate his general theory of relativity, the theory of a curved space whose geometry is determined by the presence of mass and energy. Chapter 8: Invisible Forces. After Gauss had surveyed the Earth and explored the geometry of curved surfaces, his restless mind turned to a new, mysterious phenomenon: magnetism. The force that aligns a compass needle to the north had been known for centuries but was still poorly understood. It was an invisible force that seemed to act over long distances, a puzzle that fascinated physicists and philosophers alike. Around the year 1831, one of the most fruitful scientific collaborations of the 19th century began in Göttingen. The young, brilliant experimental physicist Wilhelm Weber was appointed to the university, and he and the aging Gauss became close friends and research partners. It was the perfect fusion of theoretical genius and experimental skill. Gauss's approach to terrestrial magnetism was typical of him. First, he wanted to measure precisely. He developed a new, highly sensitive magnetometer. It consisted of a heavy magnetic bar, suspended from a long, thin thread, which could swing freely. The oscillation period of the magnet depended on the strength of the local Earth's magnetic field. To read the tiny deflections of the magnet, he attached a small mirror to it. This mirror projected the image of a scale, which he observed through a telescope onto the wall. This arrangement, known as mirror reading, was so sensitive that it could register even the tiniest fluctuations in the magnetic field. Their research required a disturbance-free location. Since even the smallest amounts of iron could interfere with the sensitive measurements, Gauss built a special, completely iron-free observatory in the garden of the main observatory, made only of wood and copper. From here, they conducted systematic measurements of the Earth's magnetic field for years, analyzed its daily and annual variations, and developed a comprehensive mathematical theory to describe the field of the entire Earth. But their collaboration led to an even more spectacular invention. to coordinate their measurements between the observatory and Weber's physics laboratory in the city center. They needed a way to communicate quickly. They stretched a wire over the rooftops of Göttingen, a distance of about 1.2 kilometers. In 1833, they built the world's first functioning electromagnetic telegraph along this wire. Imagine this: 2 wires, supported by the towers of St. John's Church, connecting the 2 institutes. At each end is an apparatus. The transmitter is a large coil into which a magnet can be moved. This movement induces an electric current in the wire. At the other end, the receiver, this current flows through another coil in which a magnet is suspended, basically a galvanometer. The incoming current pulse deflects this magnet from its resting position to the left or right. Through a pre-agreed combination of positive and negative pulses, they could transmit letters and entire words. The first message transmitted was Wissen vor meinen, Sein vor scheinen, knowing before opining, being before seeming. It was not a commercial telegraph like the later one by Samuel Morse, which was much more practical with its simple dots and dashes. But the Gauss-Weber telegraph was a working proof of principle, a direct application of the newly discovered laws of electromagnetism. To elevate their research to a global level, Gauss founded the Magnetic Association. This was a network of observation stations around the world, from Dublin to Toronto, from St. Petersburg to Cape Town. All these stations conducted coordinated measurements of the Earth's magnetic field at the same time, with identical instruments and according to the same methods. The collected data was centrally analyzed in Göttingen. This was one of the first major international scientific collaborations in history, a forerunner of modern global research projects. The old, reclusive professor in his small university town had spun an invisible web around the entire globe to fathom the secrets of one of nature's most fundamental forces. Chapter 9: The Non-Euclidean Intuition. We now come to one of the most profound and at the same time most hidden chapters in Gauss's scientific life. It is a journey to the outermost limits of thought, into a world so radically new that Gauss himself shied away from revealing it to the public. It concerns the very foundations of geometry, a 2,000-year-old riddle known as the parallel postulate. Ever since the Greek mathematician Euclid wrote his Elements around 300 BC, all of geometry was based on 5 fundamental assumptions, the axioms or postulates. The first 4 are simple and self-evident, for example, that a straight line can be drawn between any 2 points. The 5th postulate, however, is different. It is longer, more complicated, and feels less self-evident. In its modern form, it states, for a given line and a point not on the line, there is exactly one line through the point that is parallel to the given line. For 2,000 years, mathematicians tried to prove this postulate from the first 4. They were convinced it had to be a logical consequence of the other axioms, not an independent fundamental law. Countless attempts at proof were made, and all of them failed. Even as a young man, Gauss had grappled with this problem. But he took a different path than his predecessors. Instead of desperately trying to prove the postulate, he began to play with the thought, what if it were false? What if, through a point outside a line, there were either no parallel lines or infinitely many? He tried to derive a contradiction from this new assumption, but the longer he worked on it, the clearer it became to him that no contradiction emerged. Instead, a completely new, self-contained, and logically consistent geometry unfolded before his inner eye, a non-Euclidean geometry. Imagine a curved world, the surface of a sphere. Here there are no parallel lines at all. Every straight line, a great circle like the equator, intersects every other straight line. The sum of the angles in a triangle is always greater than 180 degrees. This is a model for an elliptic non-Euclidean geometry. But Gauss also thought about the other case, the hyperbolic geometry. In this world, there are infinitely many parallel lines to a given line through a single point. The sum of the angles in a triangle is always less than 180 degrees. It is a world that is difficult to imagine, a kind of saddle surface that curves into infinity in every direction. Gauss was convinced of the logical possibility of this new geometry. He was perhaps the first person to clearly recognize its existence, but he published nothing about it. In his letters to friends, he only hinted at his discoveries. He wrote that he feared the clamor of the Boeotians, The Boeotians were a people in ancient Greece considered uneducated and backward. Gauss was afraid of the misunderstanding and ridicule of established philosophers and mathematicians, who saw Euclidean geometry not just as a mathematical theory, but as an absolute God-given truth about space. The idea that the space we live in might not follow Euclid's laws was so revolutionary, so disturbing, that he did not dare to say it out loud. He kept his deepest thoughts to himself, entrusting them only to his notebooks and a few close friends. It was not until decades after his death, when other mathematicians like Janos Bolyai and Nikolai Lobachevsky independently reached similar conclusions and courageously published them, that Gauss's notes were found. It was then realized that he had been decades ahead of them all. In the silence of his study, he had carried out a revolution in thought, but the world was not yet ready for it. This episode shows a fascinating side of Gauss, the radical thinker who was at the same time so conservative and cautious that he kept his greatest and perhaps most profound discovery hidden. It was a treasure he had unearthed, but one that seemed too precious or too dangerous to share with his time. Chapter 10: The Final Years and the Legacy. The last decades of Carl Friedrich Gauss's life passed in external tranquility. He continued to live and work in Göttingen, an almost mythical figure, the undisputed Princeps Mathematicorum, the prince of mathematicians. He rarely left his city. His world was the observatory, his library, and his study. His productivity hardly waned even in old age. At over 60, he learned Russian to be able to read the works of Lobachevsky in the original, and he corresponded with scientists all over the world, often in perfect Latin. His judgment was feared and respected. A word of praise from Gauss was the highest honor a young scientist could receive. He remained a man of order and discipline. Every day he dedicated a portion of his time to pure numbers. Mental arithmetic was a form of mental hygiene for him. Even in old age, he could perform complex calculations with a speed that astonished others. He also remained a conservative mind, suspicious of the political unrest of his time. When in 1837, 7 Göttingen professors, including his friend Wilhelm Weber, protested against the new king's repeal of the Constitution and were subsequently dismissed, Gauss held back. He sympathized with them, but as a duty-bound civil servant, he avoided any open confrontation with the authorities. In his final years, he continued to engage with a wide range of topics, from improving lenses for telescopes to the finances of the pension fund for the widows of Göttingen University professors, for which he performed actuarial calculations. His mental clarity remained with him until the end. On February 23, 1855, Carl Friedrich Gauss passed away peacefully in his armchair at the Göttingen Observatory at the age of 77. His life, which had begun in a humble cottage, ended at the center of the scientific world he had helped to shape. At his request, his brain was removed and preserved. It was studied repeatedly over the decades in the hope of finding the anatomical secret of his genius. A brain with an unusual number of convolutions was found, but it provided no definitive explanation. The true legacy of Gauss lies not in his physical substance, but in the immortal world of his ideas. When we look back at his work today, its ubiquity is astonishing. The Gaussian bell curve, or normal distribution, is the foundation of modern statistics, describing everything from the distribution of heights to measurement errors in experiments. The method of least squares, which he used to find series, is a standard tool in all natural and engineering sciences. When your smartphone determines your position via GPS, it is essentially solving a system of equations based on principles Gauss developed while surveying Hanover. His work on differential geometry was the mathematical language Albert Einstein needed to describe the curved space-time of general relativity. His research on magnetism laid the groundwork for electrodynamics, and thus for all of modern electrical engineering. The number theory he established as Queen is now at the heart of modern cryptography, which secures our digital communication. Gauss's legacy is not just a collection of theorems and theories. It is an attitude, an ethos of scientific work, the unconditional demand for logical rigor, the combination of the deepest theory with the most precise practical application, and the humble recognition that behind the visible world lies a deeper, mathematical order. The story of Carl Friedrich Gauss is the story of a mind that not only observed the world, but understood it in its fundamental structure, and in doing so, changed it for us all. Outro. The story of Carl Friedrich Gauss. A journey comes to an end. We have now reached the end of our nightly journey. A journey through the life and thought of Carl Friedrich Gauss. We have spanned a wide arc, from the dusty village school in the Duchy of Brunswick to the observatories and peaks of Europe, from the most intimate secrets of prime numbers to the global forces of terrestrial magnetism. We met a boy who amazed his teachers and a man whose mind recast the foundations of science. Take another deep breath and let the impressions of this journey resonate within you. The story of Gauss, as we have seen, is a story of quiet revolutions. There were no loud shouts or dramatic gestures. The upheavals took place in the focused silence of a study, in the soft scratching of a pen on paper, in the patient observation of a point of light in the night sky. It is a reminder that the deepest changes often begin in secret, in the persistent work of a single mind that dares to see the world differently. We have seen the importance of circumstances, the foresight of a teacher, the generosity of a duke, that allowed an extraordinary talent to flourish in the first place. It is a reminder of how much potential lies dormant in all of us, and how important it is to recognize and nurture these sparks. We have also come to know the many facets of a genius. The pure mathematician who saw in number theory an art form of the highest aesthetic. The practical astronomer who calculated the orbits of the planets with unprecedented accuracy. The tireless geodist who surveyed the land with a heliotrope in hand. The innovative physicist who sent the first telegraphic message with wires over the rooftops of Göttingen. And finally, the secret revolutionary who glimpsed the possibility of a non-Euclidean world, but hesitated to share this idea with an unprepared world. This versatility shows us that the boundaries between pure and applied science, between theory and practice, are often artificial. In Gauss, everything flowed together. Practical work raised deep theoretical questions, and the most abstract theories often found unexpected practical applications. His life story is also a profoundly human story. It tells of personal happiness and deep sorrow, of the joy of scientific discovery and the fear of misunderstanding from one's peers. It shows us a man who, despite his superior intellectual abilities, remained bound by his time and its conventions. A man who saw through the universe but preferred to avoid the political storms of his age. As you now slowly drift into sleep, perhaps take with you the thought of the quiet power of persistence. Gauss's life was not a short, bright sprint, but a long, enduring marathon of thought. His 8 proofs for a single theorem, his decades of work surveying a kingdom, his tireless calculations, all of it testifies to a patience and a dedication that have become rare in our fast-paced world. It is the comforting realization that the truly great things take time. The seeds of knowledge that Gauss sowed over 200 years ago continue to sprout and bear fruit today in technologies and sciences he could never have imagined. Thus, the circle closes, from the child who taught his teachers, to the teacher who still teaches us all today, about the world, about science, and about the infinite possibilities of the human mind. Sleep well. That was today's night lesson. Thank you for listening. If you'd like to see more videos like this, please leave a like and subscribe to the channel. Good night and sleep well.